The Ising or Ising model is a model in classical statistical mechanics which describes simple degrees of freedom, the simplest non-trivial degrees of freedom, and they are just spins, and the spins can take on values +1 or -1. So we have a spin Si, that's the ith spin, and it takes on the values + or -1. Now spin thinks that that suggests that we are really dealing with actual spins. That's not the case generally, because the Ising model can be applied to many different models wherever there are only two values possible for a degree of freedom, then it can be described by an Ising model. And we shall stick here to the original formulation of the Ising model, and we will also formulate it in 2 dimensions in order just to explain how the model works. And the model is defined. I will now take just a simple square lattice in 2 dimensions. So these are the lattice sides, and on each lattice side we have a spin, and the spin can have a value up or down, or it's +1 or -1, and I will indicate that now by a thick plus if it's +1 or a minus if it's -1. So at each side we can put either a plus or a minus, and so on and so on. Now this model is described in fact by a Hamiltonian, which tells you which configurations of spins are favorable and which aren't. And that Hamiltonian has the form H is minus k times a sum, and then we have here a special notation which I'll come back to, as I as j, and then minus h si. So this is the Hamiltonian, and the notation means the following of these angular brackets. Angular brackets I and j means nearest neighbor interaction. So that means that I should be a nearest neighbor of point j. For example, these 2 spins are nearest neighbors. And this first term tells you that you get an energy bonus. You get a negative energy when the 2 spins have the same value, and it doesn't matter whether they are 2 minuses or 2 pluses. In each case you get a negative contribution to the total energy. And then the second term describes the effect of a magnetic field, that's the H, and the magnetic field will favor the spins to be up or to be minus. So the first term is symmetric with respect to the spin direction. If I would flip all the values, because this is a quadratic term, it doesn't change the Hamiltonian. The K gives you the coupling constant, so it tells you how much energy you gain by having like nearest neighbors, and how much energy you have to pay for 2 unlike nearest neighbors. Now we ask ourselves the question, what would be the typical configurations of this model described by this Hamiltonian as a function of temperature? So what are the representative spin configurations for different temperatures? And we do that first for h equals 0. And starting then with absolute 0, we know that the energy wants to be absolutely minimal, and we can reach that minimum by having like spins everywhere on the lattice. So there are 2 solutions here: either all the spins are plus or all the spins are minus. And on the vertical axis here I'm going to indicate what the magnetization of the lattice is, and the magnetization is defined as the number of spins plus minus the number of minus spins, and we divide that by the total number of spins n. And so if all the spins are up, then n plus is equal to n. This guy is 0, so we get +1. And if all the spins are down, then we have -1. And so this is the m-axis here. We can also guess what would happen at an infinite temperature. We know that all the configurations are weighted by the Boltzmann factor minus beta times h. So at infinite temperature, if T goes to infinity, then we have that beta is 0. And so it doesn't matter anymore what the spins do. The Boltzmann factor for every configuration is the same. And that means that the spins can all be chosen randomly, and therefore on average we expect for high temperatures the magnetization to vanish. So this is what we expect at high temperatures, and now we can guess what happens in between. In particular, we could start at T is 0 and then ask ourselves what would happen if we increase the temperature a little bit. So we shake the system. It consists of all pluses or all minuses, and we start shaking the system, and then you can imagine that sometimes one of these spins will flip to a different value, and therefore the magnetization will slowly decrease if we started from +1, and it will slowly increase if we started from -1. So this is the behavior that we will expect for low temperatures. And now, if you would be to fill in the behavior in between, it would be very tempting to draw two curves like this. The magnetization gradually goes down, and then it reaches 0 at infinite temperatures. And this is not a very successful attempt at making these two curves symmetric, but I suppose you grasp the idea. Now, the Ising model was solved exactly for zero magnetic field in 1944 by Lars Onsager, and it turned out that this picture is not correct. The actual magnetization as a function of temperature can be seen here, and beyond this point, which is the point of a phase transition, it is strictly 0. So we see that there is here really a sharp angle in the curve of the magnetization as a function of temperature, which is non-analytic behavior, which was quite a point of discussion because the model itself is defined as a simple analytical model. So how can we get non-analytic behavior? Well, that turns out to be related to the fact that the solution is for an infinite number of spins, and so for any finite number of spins you still have here a smooth behavior, but that behavior gets sharper and sharper if you send the number of particles to greater and greater values, and if you in the end reach infinity, then this is really a cusp, so non-analytic behavior. And so it's important to recall this was a great achievement in 1944 by Lars Onsager to solve this model analytically. That solution is quite difficult, and therefore it's useful to see whether we can find, say, an approximate solution to see what the behavior of the model is. The Onsager solution predicts the phase transition to take place precisely when the coupling constant divided by kBt is equal to 0.44. So it's interesting to spend a little bit of time to that. So we see that the Hamiltonian only has one parameter once h is 0, and that's the parameter k. And you see that in the Boltzmann weight, this parameter only occurs together with 1 over the kb t. So it's always multiplied by beta. And that's why the behavior of the model does not depend really on k, but it depends on k and t together, but only through the combination beta times k, so k over kt. And that value at the phase transition is 0.44 and something. So let us see what that gives when we really look at the model. So I've written a small simulation for the Ising model where we take this parameter k over kt, we start on the right hand side, then it's a little bit smaller than 0.44, and then we decrease the temperature, so the parameter is going to get bigger and bigger, so we move in this direction. So here you see the model at high temperature, and you see that the spin ups are, for example, blue, the spin downs are red, and you see that on average the system is neither blue nor red, so it's neutral. There are as many pluses and minuses. The temperature is still above the critical temperature, so the coupling constant is still less than 44, but we are approaching that value, and if you watch the simulation carefully, you see that the areas where you have only one color, they grow and they grow. They get larger and larger when the temperature is decreasing. So now we are nearly there, 0.41, and you see that now you have also long spells where a majority of the spins is blue and where a majority of the spins is red. So also the time of fluctuations is increasing. We have now reached a value of 0.43, and now we have crossed the phase transition, and now you will always see that the value of the spins is a majority red. So there are indeed blue islands occurring in a red sea, but the majority color will no longer change. And you also see that the islands of spins having a different value, they shrink in size with decreasing temperature. And so there is a larger and larger majority of the spins which has the dominating red color. It is important to scan slowly through that critical temperature, because otherwise one half of the letters may end up being blue and the other one half may end up being red. That's not an equilibrium situation. What you are looking at now is typical for the equilibrium Ising model. And that should be enough to have an impression of the behavior of the Ising model at zero magnetic field. So what happens when we switch on a magnetic field? Then the picture changes somewhat. So suppose we switch on a small positive magnetic field H. That would help the plus spins because that lowers the total energy. And that means that in this picture, the +1 phase, which we have here, has a lower energy and a lower free energy than the -1 spins and phase, and that always holds. So there is only one stable curve. There are not two phases that are completely equivalent. There are two of them, and the way the picture changes is the following. We find a positive magnetization, and the cusp will also disappear, and so for each finite temperature there is a finite value of the magnetization. So the red curve here is the curve corresponding to a small but positive magnetic field. So the most interesting case is when the magnetic field vanishes, because in that case we have a phase transition. Now we return to the H0 case, where we have a phase transition, and we try to quantify the behavior close to the phase transition. Now, without derivation, we can identify certain behaviors that we will analyze later in more detail. And one of those is the way the magnetization vanishes when we approach the critical point. So this phase transition here is called a critical phase transition, and it takes place at Tc, and we are interested now in how this curve behaves when we approach Tc from below. So T is going to Tc from below, and we ask ourselves what the magnetization does. Well, it turns out that the magnetization as a function of T behaves as Tc minus T in the power to some power, which is beta, and this should be just a proportional sign, and that beta turns out to be 1/8 for the Ising model. And so this is just one example of a so-called critical exponent. There are more examples, and one is the behavior of the susceptibility. What is the susceptibility? The susceptibility is defined as dm/dh. So it tells you that if I switch on, in this case, a small magnetic field, how the magnetization then starts rising. So normally we would expect that that would be linear, so that we would get some constant depending on temperature. But it turns out that when we approach the critical point, this is different. So we calculate this at a particular t, and then it turns out that this behaves as T minus Tc to some power gamma, and this gamma turns out to be 7/4 in the case of the Ising model. Then we have the specific heat at a constant magnetic field, Ch. It also depends on the temperature, and that behaves like T minus Tc to the power alpha, where alpha is 0, which means that we have a logarithmic singularity. The logarithm has a divergence which is weaker than any finite power. Other critical exponents are those of the magnetic susceptibility, Km, which tells us how the magnetization changes with field. We evaluate that for zero field, so if we switch on a weak magnetic field, how does the magnetization then increase? So that's what happens here. The red curve is with a small field, and this red line here corresponds to zero magnetic field. And then if we calculate how this variation depends on T, we get T minus Dc to the power minus gamma, where gamma is 7/4 in the case of the Ising model. And the specific heat at constant field, that behaves like T minus Dc to the power minus alpha, where alpha is equal to 0, and alpha is 0 doesn't mean that there is no dependence. It is a logarithmic dependence because the logarithm has a singularity that is weaker than any power. Finally, we can consider what happens when we are at T is Tc. We switch on a magnetic field, and then the magnetization, it is not varying linearly with the magnetic field, but it increases with some power, h to the power 1/delta, and this delta is 15. So we see that all these critical exponents have very simple values, 1/8, so they are simple fractions, 7/4, alpha is 0, and delta is 15, and that may be ascribed at first sight to the fact that we look at this simple model on a square lattice, and in fact it turns out that it does not depend on that. So if we switch on next nearest neighbor interactions, so for example this spin can not only talk to its direct neighbors but also to next nearest neighbors, that's an example of how we can distort the Ising model, and it turns out that the critical temperature then shifts to a different value, but all these critical exponents, they are pretty robust. We can change quite a few details of the model without changing the critical exponents, and this phenomenon is called the universality. So the critical exponents, they are universal, and we can change quite a few details in the model without changing the critical exponents. Calculating the partition function for the Ising model in 2 dimensions is a formidable task. However, it is possible to analyze some of the essential features of the phase transition using some approximations, and then of course the question is whether the critical exponents that we find after these approximations are the correct ones. The approximation, which is very popular and not only for the Ising model, is the mean field analysis, the mean field model. So we start from the full Hamiltonian and try to reduce it to a simpler form, and that simpler form is obtained by introducing a fluctuation of the spins with respect to the average magnetization, and we obtain that by just subtracting the average magnetization from SI and then adding it again, so that the expression does not change. And we do the same for the Sj, and here is still the magnetic field acting on the spins. We can then rework this expression as follows. We split these monomials into 2 parts. One part is the deviation of the spin from the average magnetization, and then we have the magnetization. And so first I get the 2 deviations multiplied by each other, then I have the cross terms, these two, and finally I have a term minus km squared, and then there is the term with the magnetic field. And now we assume that m is indeed the magnetization, it's the average value of the spin over the lattice, n is the total number of sites on the lattice, and we assume that each spin has q neighbors. So q neighbors are present per spin. In a 2-dimensional Ising model, that means that each spin of course has 4 neighbors, 4 nearest neighbors, and therefore q is 4 for the 2D square lattice. Now we make the major step to neglect the contribution of the first term, and the justification is that this is a fluctuation from the average behavior squared, because this is a fluctuation and that's a fluctuation, it's deviation times deviation, and we assume that that is small. We will come back to that approximation later on. And that means that all the other terms are linear in the spin, and we can exactly solve problems that are linear in the spin. But of course there is a snag here. We have everywhere used this m, which is the average value of the magnetization, and we do not yet know what this m value is, and so that should come out of the solution of the model. So we then focus on the remaining terms, and the remaining terms are collected here. So we have here a sum over all the nearest neighbor pairs times m squared, and there are 2 terms which are identical coming from this and from this, and they both have a plus sign, so they compensate half of those compensate for that term, and I'm left with a plus k times m squared. And then we have an si times m plus an m times sj, so they are collected here, and then I have the magnetic field term. So realizing that this sum is the same as that sum, we can move them together. That gets rid of the factor of 2 here, and we have a minus kqm times the sum over the si's. Then we have this term and the other term, which are still the same as on the previous line. So the next step is to calculate the partition function which is the sum over all the configurations of the spin. So for each spin on the lattice, we have to sum over that spin being plus or minus, and then we take e to the power minus beta times the mean field Hamiltonian, for which we take the last form we arrived at. And if we work that out, we simply get this expression. Here is this energy term which comes in front of the sum over all the spin configurations. We rewrite the sum over all the possibilities for all the spins as a product over I, as I summed over the values plus 1 and minus 1. And these are all the values occurring in the exponent, which are proportional to the SI. And we can immediately see that this gives us 2 to the power n e to the power minus beta kn q m squared times the cosine of beta times kqm plus h si. So we have the argument here now occurring in the cosine, which appears with this factor of n. And so we can calculate then also the F, that's the free energy, and let us divide it immediately by n. Gives me minus kBt over n of log z. And the result is then this expression, where we first have an energy term, and here this looks like a entropy term. It is also easy to calculate the average value of the spin on each side. So that's my m, and that is calculated as follows. All the spins are independent, so I just have one expression per spin. This is the Boltzmann weight, and in the numerator we multiply that by SI, and in the denominator we just normalize by the sum of the two factors, and we see immediately that this gives us a tangent, a hyperbolic tangent of beta k q m plus h. So we see here how we can calculate the magnetization arising from this model, because we say that m is a function of m that has the form of a self-consistency equation that we can solve, and it is useful to solve it using a graphical approach. We analyze the model for zero magnetic field, h is 0, and we define the coupling constant as beta times k. So k is the bare coupling constant that occurs in the original Hamiltonian, and we multiply that by beta because it's only that combination which occurs in the Boltzmann factor. And in that case, this self-consistency equation acquires the form m is tangent h, the hyperbolic tangent of j times q times m. So let us see how the solution proceeds in a graphical approach. So the dotted line is the line m equals m. So here we have m. And then we see for different values of qj the arctangent. And we see that two things can happen. So for qj, when it has small values that corresponds to high temperature, then there is only one intersection, so there's one point where this value can be equal to that one, and that's the value m is 0. If we are at low temperatures, then we find two intersections. For example, the dashed line has two intersections with the line m here and there, and so those are two magnetizations close to +1 and -1. So if we now try to relate this plot to the phase diagram of the Ising model, then we can draw some interesting conclusions. For low temperatures, we see that there are two values of the magnetization which are opposite. That's the situation when we have the two intersections of the arctangent with this line. For high temperatures, if we are on this side, then there is only one value for m possible, and that corresponds to this line, which is only the m is 0 intersection. So where is the critical point? Well, if we increase the temperature, then this arctangent is going to have a flatter and flatter shape, and then when finally it just touches this line, so when it's parallel to this line at m is 0, then is the point where exactly these two intersections have merged, and beyond that there is only one point. And that's precisely when qj is 1, because the slope of the tangent of the hyperbolic tangent is 1 as a function of this argument, and therefore if qj is 1, we find that the two slopes of the two curves are identical at m is 0. Now we can use the self-consistency equation to find the critical exponent beta. Remember that the critical exponent beta gave you the shape of this curve. So we had for small values of the magnetization, when we approach Tc, the critical temperature from below, the m behaves like Tc minus T to the power beta, and that beta had a value of 1/8 according to the exact solution of the Ising model. So let's see what we find in the case of the mean field solution. Well, the value of m is close to 0 because we are close to the critical point, and therefore we can do a Taylor expansion of the tangent of the hyperbolic tangent on the right hand side. And so what we obtain then is qjm minus one third qjm to the third. This is the Taylor expansion of the tangent hyperbolic, where we have kept only the lowest two non-zero terms. So moving the term with the m to the third to the left hand side, we can write it in this form. Then we divide out one factor of m on both sides, and we see that the m squared is proportional to qj minus 1. Now when qj equals 1, then we have the critical, that we are exactly at the critical point. So we can write this as qj minus qj critical. And we can also write that as qk divided by kbt minus qk divided by kbtc. In other words, the m squared is proportional to 1 over t minus 1 over tc. And that essentially goes like tc minus t over tc, or over t. And that means that the m is proportional to tc minus t to the power 1/2, and so we find beta is 1/2, in contrast, quite a sharp contrast to the exact solution, so we are quite far off. And that is equal to tc minus t over t times tc, and so therefore this is essentially proportional to tc minus t. Now you may be wondering what I mean by essentially proportional. Well, m squared is going to 0, and indeed when t approaches tc, this numerator vanishes, and so the denominator is tc times tc and a little bit, and therefore we don't care really about the denominator, because we are only interested in with which power m is going to 0. And we see that that power is like tc minus t 1/2, and therefore we see that the beta that we get from mean field theory is 1/2, and that's in sharp contrast with the exact solution. By the way, in case you may have been confused so far, the beta here is a critical exponent and you should not confuse it with 1 over kt. So this beta is just a number. We see, by the way, that the critical phase transition in this case always occurs at qj is equal to 1, and therefore we see that the j critical is 1 over q, and that's 1 over 4 in the case of the 2D square lattice. And you should compare that with the value of 0.44, which is the exact result following from Onsager's solution. The other exponents can be calculated in an analogous way, and we find then for the magnetic susceptibility that it scales like t minus dc is minus 1. This exponent is called gamma, so we find gamma as 1, which in the exact solution turns out to be 7 over 4. The specific heat makes a jump at Tc, and it goes like t minus dc times up to the power an exponent alpha. That exponent alpha is a 0. In the exact solution it's 0.2, corresponding to a logarithmic singularity. And if we are at Tc and switch on a small magnetic field, then the magnetization varies like the field to the power 1/3. This value 3 is called the exponent delta. Delta is a 3, which in the exact solution is 15. So in the two-dimensional Ising model we find critical exponents in mean field theory which deviate substantially from the exact values. It turns out that if you go to d is 3, the situation is a lot better. So if you go to the three-dimensional Ising model, you find better values for the critical exponents. An example is the value beta is 0.324, which is the exact value, and in our case that's already a lot closer to our 1/2. If you go to d is 4 and beyond, or if you go beyond d is 4, which of course is rather theoretically but very important case, then it turns out that you recover all the mean field critical exponents, so they become exact if you go beyond 4 dimensions. Why is the mean field theory more reliable in higher dimensions? Well, that is related to the fact that it's based on a neglect of fluctuations, and if a spin has only a few neighbors, then the fluctuations of that spin can be substantial, and so our neglect of those fluctuations is in that case not justified. If however we have something like a three-dimensional model where each spin has 8 neighbors, then the fluctuations of the spins are much less, because the spins keep each other better at a certain value. And another way to say that, to phrase that, is the following. Here we have returned to our mean field Hamiltonian. And so imagine that the magnetic field is 0. This is a constant term, and in fact we have replaced the interaction of a spin with its neighbors by the average spin. That's what we do here. And you can imagine that if there are many neighbors, then the average value of those spins, of those many neighbors, will be much closer to m than if there are only few neighbors. And so that also gives you a feeling for the fact that it's much more justified to neglect the fluctuation terms in higher dimensions than it is for low dimensional systems. So mean field is a reliable approximation for systems in many dimensions. However, it fails dramatically in 2 dimensions. Finally, I'd like to explain a rather quick and easy way to find the self-consistency equation of a spin. This method, however, doesn't give you a good approximation for the free energy or a good formulation of the free energy, but the self-consistency equation can be found rather easily. So here we have the Hamiltonian of the Ising model with the nearest neighbor interaction and the magnetic field. So let us now draw the lattice together with the spin Si. So here you see a fragment of an Ising lattice with the side I in the center, and on the side I we're going to place a spin, the spin Si. And the spin Si talks to 4 nearest neighbors, and I indicate those interactions via blue links. And so the Si talks to these spins at these neighboring positions, and the mean field step consists now in changing the Hamiltonian by imposing a value of m, which is just the average magnetization at the 4 neighboring spins. I don't care so much about the other values, but I put a value m here. And so our mean field Hamiltonian can be written as in H0, which contains all the couplings except the 4 blue couplings, plus, and then we have a blue Hamiltonian, which gives me the interaction between side I and its 4 neighboring positions, where the 4 neighboring positions are assumed to have a spin value which is fixed at m. We know exactly what the Hi is. It's the coupling between spin Si and its 4 neighbors, which have a value of m. So we have minus 4 times k times Sim. And more generally, if there are q nearest neighbors, I mean this is not specific for the square lattice in 2 dimensions. In general we have just minus q k Sim, where q is the number of nearest neighbors of each side. So if we now want to calculate the expectation value of the spin at side I, we can write this in the following way. It is the standard expression, and what we have achieved now is that this Hi, because we have chosen the m to be fixed, removes the couplings between Si and other spins, and so this simply reduces to the following expression. The H0 has disappeared from the problem, and using now the straightforward representation of Hi, which is now simply minus qk Sim, and putting that in, we directly find that the expectation value for Si is given by e to the power beta qkm minus e to the power minus beta qkm, where this minus sign is due to the fact that the Si assumes a value of minus 1, and in the denominator there is no Si, so both terms have a plus sign. And we know that we can rewrite this as the tangent hyperbolic of beta qkm, and that is the result we had already arrived at before. So the self-consistency equation has now simply been found as this m is tangent h of beta qkm. And this way of finding the self-consistency equation can easily be transferred to other models, so models on different lattices or with different spin values. And that concludes the discussion of the Ising model.